Hi there, this is my English speaking practice, and I'm solving coding problems on LeetCode. And today I'm gonna about study about patterns to solve problems. Yeah, since I had trouble with this problem, it's kind of divide and conquer problem. So I want to organize the solutions for patterns. Okay. Example, it's there are some patterns. Conquer, divide and conquer, and greedy, and yeah, and permutation. Yeah, these problems similar. Yeah, these problems have similar problem statements, right? So we have to we have to know what is the best way to use. Okay, so from now I want to organize these patterns. So what kinds of problem statement, what kinds of problem, and what kinds of problems we should take dynamic programming, or greedy, or divide and conquer, or permutations, backtracking, right? We have to tell which is the best. Okay. Yeah. Okay, so I will ask ChatGPT. Organize I want to be able to which is the best way when I work on these problems. I want to organize solutions for the following problems. They share similar problem statements, so I want to figure out which approach works best when I face these kinds of problems. I've noticed that some problems kinds of look the same, but the best way to solve them can be totally different. So I want to organize them by approach, like when should I use DP or greedy or divide and conquer, or maybe backtracking with permutations. The problem has overlapping subproblems. You keep solve the same similar problem. The problem has optimal substructure. You can build an optimal solution from. Greedy. You can make a locally optimal choice at each step and still end up with global optimal. Okay, divide and conquer. The problem can be split into independent subproblems. You can combine their result to form the answer. You need to try to all possibilities. Solution space can be pruned with constraints. So I want to find a similar structure and understand. Can be solved with several approaches, so I want to find a common structure behind them and understand it. Many problems can be solved using multiple paradigms, and the trick is to recognize the underlying structure that makes them related. Yes. So dynamic programming, you build up from smaller subproblems and divide and conquer. You can also write a recursive function that splits into two paths, left and down. Backtracking, you can brute force paths that take the mean. Each stage depends on choice from the previous step. It's a tree decisions. DP is just a compressed, optimized version of backtracking. Try to ask yourself, does the problem visit subproblems? Revisit subproblems. Can I make independent splits? Can I make locally optimal choices safely? Do I have to explore all possible states? Sometimes the same recursion tree can be optimized differently. Would you like me to show a visual comparison? Or how? Yes, please. We will use a simple but powerful example, minimum path sum. Minimum path sum is I solved it. This. No. What? Because it clearly shows the evolution from brute force backtracking, DP, and greedy. Okay, though greedy doesn't always apply here. Okay, problem examples: given non-grid numbers, find a path from the top left to bottom right that minimize the sum of natural or numbers on the path. You can only move right or down, brute force and backtracking. We try our possible paths. It's like exploring every branch to binary decision tree. I see. Explores every possibility, many repeated sub-problems, huge overlap. So every call function in the function it called next function twice. So yeah, it's the number of calls increase to exponentially power of 2 power of n, right? Okay, and sometimes it points the same cell, so yeah, there are many repeated sub-problems, huge overlap. Yeah, the time complexity can be O of 2 power of n plus n, exponential algorithm. And this version just explored all possible paths recursively. It works conceptually, but it's super slow because it redoes the same work many times. With memoization top-down DP, we notice the same ij is computed repeatedly, so we cache results. If there is there is result computed results, we return it. Yeah, that's it. Just that's it. Still recursive but avoids recomputation, turns exponential into m times n. Here I'm doing the same recursion, but I remember the results for each position. That way you don't have to redo the same calculation again and again. Yeah, seems good. Bottom up DP, iterative. We realize each cell depends only on its top and left, so we can fill the grid directly. That means update the grid. It depends on the previous and top and left cells. Same sub-problem structure, no recursion, very efficient and clean, space optimized if needed. Space optimized. If this version, we fill up the grid from top left. Structural insight. All these methods share the same recursion formulas. The only difference is how we handle overlap intervals, recompute, store, iteratively, skip global check. A greedy approach will be at each step move to the smaller neighbor, right? However, it doesn't always give the global minimum. Yeah. You might think okay, so my understanding. Do we of course if we generate all possible nations, we can solve it, but it's not optimal. And more complicated than it should be. Do we have to generate all possible combination? Of course, if we generate all possible combination, we can solve it, but maybe it's not optimal and more complicated than it should be. Revisit sub-problems. Independent splits. Difference between independent splits and no. splits and what independent split means. An independent split happens when divide data or such space into smaller parts. Each part can be solved independently without needing results from the others. After solving them, you just combine, merge, concatenate, sum, etc. the result. Yeah, I know. The subproblems mean that subproblems appears when smaller parts of the problem overlapping or subproblems are not independent. Overlap. I see. When the smaller part doesn't share any data, that's an independent split. You can just solve each half separately and merge the results. But when smaller parts overlap or depend on each other's results, those are subproblems, and that's when dynamic programming becomes useful. Would you like me to show a short code example comparing both? Yeah. I So in my words, I call it subproblems, regardless of they are dependent or independent. Okay. And or greedy. If we can choose local optimal, and it makes global optimal, we use greedy. Otherwise, we use dynamic programming. Look at we sub-problems and small problems. In my words, I call them sub-problems regardless of they are independent each other or not. So there are two patterns: independent sub-problems use divide and conquer, dependent sub-problems use dynamic programming or greedy approach. If we can choose local optimal and it makes global optimal, we use greedy. Otherwise, we use dynamic programming. First, ask, do we need to generate all possible combinations? Of course, if we do that, we can eventually solve the problem, but it's often not optimal and can be more complicated than necessary. If the answer is no, then we should focus on smaller problems and try to build the solution from them. In my words, I call these smaller problems sub-problems regardless of whether they are independent or not. There are two main patterns: independent sub-problems, then use divide and conquer. Dependent sub-problems use dynamic programming or greedy. If choosing a locally optimal option also leads to a global optimal, we can use a greedy approach. Otherwise, we should use dynamic programming. Need to remember overlapping results to avoid recomputation. I'm okay. This is one of the most fundamental conceptual links. Recursive plus memoization. Top-down dynamic program. When you solve a problem unrecursively and use a dictionary or cache to store previously computed results, you are already doing dynamic programming just in a top-down fashion. You start from the big problem and recursively solve smaller ones. Each time a subproblem's result is computed, you save it. Memoization. When the same subproblem appears again, top-down approach, bottom-up. So what's the relationship? Bottom up. Basically, recursion with memoization is just a top-down version of dynamic programming instead of filling a table bottom-up. We compute results as needed and store them in a cache. Both approaches solve overlapping subproblems efficiently. They just go in opposite directions. Okay. So October 5. Okay, let's work on ugly number. An ugly
Ugly.
Ugly number. An ugly number is a positive integer whose prime factors are limited to 2, 3, and 5. Given an integer n, return the nth ugly number. Oh. Nth ugly number. Okay. Okay. And it's not small. Okay. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. Nth. Okay, so n is not too big, so we can do it linear algorithm, linearly, I think. It's like a Fibonacci, I guess. Yes. So yeah, nth ugly number 1, 2, 3, 4, 5. Yeah. For example, 2, 3, 2, 2, 2, 2, 3, 3, 2, 5, 2, 5. And 12 is 6. 6 times 2. Okay. And this is 4. 2, 4. 4, 2. 3, 3, 5, 2. Five, 3. 8, 2. Yeah, there are sub problems. There are sub problems. How do I define the sub problems? It's yeah, we can. So maybe 2, 5, 3, 5. One, 5. Times 2 times 3, and yeah, We have three options: times 2, times 3, or times 5 for each numbers. Okay. Yeah. So okay, so the first question is, do we have to generate all possible combinations? That here all combinations means each factor. For each number, calculate all factors, but it's not optimal, so I don't need to generate all possible combinations. Yeah, we will reuse the results of computation. For example, we start with 1 and there are 3 options. We initialize the array. And yes, two, three, five, two, three, yeah. Oh, this is not good, because we don't yeah. Ugly numbers. While ugly numbers, the last index, the number at the last index in ugly numbers, that is the latest ugly numbers, the largest ugly numbers, and we compare the No. Okay. It's this is obviously dependent subproblems, and we cannot choose local optimal. We cannot choose locally optimal option, so we have to use dynamic programming and recursive memoization or table iteration. I'm thinking about table plus iteration because this is like bottom up. Seems to be a bottom up problems, but I don't know how to one, two, three, four, five. Two, three, two, one, two, one, three, two twos, 1, 2, and 1, 3. No, it's 5. 1, 5. Bottom up. We finished append the numbers that is derived from the number at index 0, because we can derive 2, 3, 5 from 1. Okay, we already appended, so index 1 is finished. And we increment the index, and the number is and So we can get 4, 6 and 10. 4, 6 and 10. So we are going to check until number 10. How about use recursive? But we cannot tell if it's the smallest number to append. So how to do that? So in this case, we have to look at like this, cause 3, 3. Oh, 2, 3, and there are 2, 3 and 3, 2. We can yeah, it doesn't work, because we have to check if it's the smallest. We have to make sure it's the smallest number to append, but it's difficult. in this case 2, 4, 6, 10. Yeah, 4 is already included, and 6, yeah, we should append 6 here, but how can we make sure that's the smallest number to append? There might be 6, 9, 15. And 8, 12, 20. Ah, okay, I see. So we should check the number at the next index times 2. That's the candidate because it's smallest. It's the smallest number that appears in the future. So if we want to think about this, about index, about the number 2, we have to think about the number at the next index times 2. If it's less than, we can append it, and we are going to go for next. Regarding 10, it's less than the it's greater than times 2, but it's already included. So we look at next. 9 is also less than the 10, so we want to we find the smaller number, so we want to append this number, but as well in this case we have to check the next index times 2, and it's 8, so we can append 8. Okay, and we can make sure it's the smallest number because it's located at the times 2 column, so 8 is the smallest number, after the base number is 4. Okay, so we can append the 8 as the smallest number and it backtracked, and we can so we try to append 9 again, and how about this? We also have to check. No, we don't have to check at the same columns because we can make sure it's a smaller. So we have we have a recursive structure. That's a base number, and we want to if no. N times 2 is the smallest. Next, try to N times 3. This argument means 2, 3, or 5. Okay, so for this function, try to append index. Index means the base number, and the core specifies the multiplier 2, 3, or 5. Okay, multiplier. So we want to index. Yeah. Yes. This is not necessary, but for my understanding, if multiplier is 2 and this condition doesn't meet, it means already included, already appended. So do nothing. If multiplier 3 we should check the number at the edx plus 1 and the multiplier is 2. We return it. Do nothing. So we check if, or we make sure Yeah. Oh, wait. We have to compare. So this case. And it's not index base number, right? What is it? This is the this is wrong. Yeah, we should compare the largest number in the array, and we should compare base times 2. Yeah. And if the multiplier is 3 and they are greater than the latest one, we should check base plus 1 times 2 if it's smaller base times 3, otherwise is this correct? I'm not sure. Three, 5, 3, 5. But it's not top down. The recursion will finish immediately. Right? Because we want to base 2, we want to append the base 2 and multiplier 3 Mm, 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 mm. Okay, so if we can append the number successfully, we call next. We are try to append the next number. So in this case, the base is same. The multiplier would be 3. In this case, base is same, and multiplier gonna be 5. This case, since we can append the multiplier with the multiplier 5, we should increment of base, and yeah, the multiplier would be 2, and that's it. Yeah, and since we already have 1 2 3 4 5, we want to 2 3 2 3. Okay. Mm. Maximum recursion depth exceeded. Really? Yeah. Oh, we didn't the didn't set the finish condition. If and return -1. Oh, n. Okay. Really? Oh, when the input. Okay. I see. So no. Greater than n. Greater than n. Hmm. 14 is wrong. Why 14? Base number doesn't increment one by one. How do I handle it? Base number. Okay, so base is like this. In this case, we want to index 1 and core index plus 1. Oh, wait. Same index. Call it with same index. EDX. Right. Let's go. Wrong answer. One, two, three, four, five, six. Oh, not 9. Why? Six. So we want to, here we want to append 9. So we look at 4, 2. So we can append 8. We can append 8. I see. After append it, we have to return. Okay, so in this case, we check, we want to append the number at next index times 2, but after that we should append this number, right? So I will use table and iterative pattern, table and iteration pattern. We start with index 1 and the multiplier is 3. we have ugly numbers array, and we want to, yeah, the target is base times multiplier, and we have two candidates. We should check ten, 15. So when we append this one, should check the next number. Should check the next number. Multipliers 0, 1, 2, so 1, 1. So in this loop, our goal is to append the target. So we have to check these two numbers. That means oh wait, 12. Mm-mm. 18, 24, we think let's simulate when appending this number. Yeah, we can access the largest number that is already appended in auxiliary nums. But in order to append this number, we have to check these numbers 10 and 15, and yeah, 10 is less than the largest number that is already in the auxiliary num arrays, so we can skip it. And next 15, let's assume this is 16, so it's greater than the largest number, existing largest number, so we can append. We are going to append this number, but in order to append this number, we have to check the next index here. Yeah, of course. And additionally, we should check this. Oh, why? So 7, 8, 16, 8, 24, 80, 40. So we should check these 5 numbers, these 6 numbers, and when we look at this number, we can finish for searching. So we have index and multiplier index. This indices the number we want to append. Okay. How about this? And in this function aims to append the target, and if it succeeds to append, we don't call the next. Yeah. Multiplier plus 1 modulo by 3, and if multiplier 0, we can increment index. This case 2, I think because this case, I mean, call 2 and then call 3, and calling 3 calls next colons next 2, right? But why we can't call this function, call this point? So so 4, 6, 8, 4, 4, 5, 6, 8, 4, 5, 6, 8. I want to append this number. Look at 5. Look at 6. Look at 8. We can notice here. That is, so in this case we want to append base times 5, the number. So we basically base index. Base plus 1, that is wrong. Because we have index, so index plus 1. That is index plus 1, that is while the number index plus 1 times 2 we have to loop it, times 3 we have to continue loop it, we have to continue right. And still the target is greater than the number at the next index times 2, we have to call index plus 1 second. This is not beautiful, but yeah. So regarding 4 to I'm not sure. Oh, correct. But how about this? Oh, correct. What? 38. I gave up. remove it from the set, insert the main. It's tricky. Heap approach and priority queue. DP. I want to see this. Okay. Yeah, DP is a optimal solution. So, okay. Here, initialize the DP array to store ugly numbers, and the first number is 1. Three pointers for multipliers of 2, 3, and 5. Okay. 2, 3, 5. And generate ugly numbers until we reach the nth one. Okay. Now find the next ugly number as the minimum of the next piles. Next piles of 2, 3, 5, 2, 3, 5. And we can append the 1 and update the corresponding pointer and the next multipliers. The next ugly number that is determined from these values, its minimum values between them, and if it is if it's same as the next pairs of 2. Okay, so if you use 2, we can really? So the first ugly number is 1. I see. So yeah, here we prepare the indices for the pointing the latest ugly number, yeah, for each 2, 3, and 5, right? And if you use the 2 next multiple of 2, we can increment the index because yeah, we already used. So update the index and times 2. That's the next one. So the idea here is for 1 we have 3 options, 2, 3, and 5. Okay, that means yeah, this line express this. Yeah, we have 3 options and choose the minimum one. Okay, so we pick 2, and after that we should update the candidates to 3, 1 because we already use 1 times 2, so the next candidate gonna be 2 times 2. Okay, 2 times 2 because this index is the minimum minimum, minimum existing ugly number. So the next multiplier of 2 gonna be 4. So we can choose 4, 3, 5. We can choose one from 4, 3, 5. Yeah. So we can append 3 and 4, 5. I see. Was difficult for me. So that is, the bottom up approach is good, was good, but the way is not good. So for each loop, we append one element. Here, we find the enumerate candidate and yep. Mean value if C mean bar update C and chosen index is J. Okay, so we can append the mean bar and chosen index is J. So indices chosen index increment and yeah, the base would be ugly nums and indices choose an index and candidates choose an index times multiplier choose an index base times earned return n -1 what? What is the difference? Ah. Four, 3, 5. Six, 6, 5. Oh. Appended the same numbers? Ah, that makes sense. But why happen? So I see. Initialize with 0 and like this. And we need to specify the index. Right. Arguinums. Okay. Why? I see. Why? Why this can avoid the duplication? Mm-hmm. What happened? Oh. Find the next ugly number as the minimum of the next multipliers. Next ugly number is equal to so index 0 we are incrementing the indices, and after that we access the multiplier, choose an index, update the candidate. Why 6? Ah, I see. Not else if, so makes sense. Makes sense. So this case we just update the place at the chosen index, but this case, for example 668, the next arguing number is 6, and this condition is true, and also this condition is true. So in this case we can update the twice if they are the same. Okay, so we cannot use this like this. So I will copy and paste and submit it. Great. Yeah. It took so long. I want to solve quickly, so let me try next question. Given an integer n, return the least number of perfect square numbers that sums to n. Perfect square number. A perfect square is an integer that is square of an integer. In other words, it is product of some integers with itself. For example, 1, 4, 9, and 16 are perfect squares, while 3 and 11 are not. Okay, so return the least number sums to n. Sums to n. Oh, really? Yeah. Does the solution assured? Can the solution be assured? I'm not sure. I don't feel like I can solve quickly. Okay, but I try to talk a lot. Perfect square numbers. Yeah, that sums to n. Okay, so but n is too large. Maybe we have to notice something mathematical something. Yeah. Mm, 12. Yeah, the maximum square number within 12 is 9. So Yeah. So first of all, do we have to generate all possible combinations? At here, all possible combinations means we all check the perfect squares within n. Okay, yeah, but obviously it's not optimal. There must be a sub problems like this, so we don't generate all possible combinations. Yeah, we focus on solving sub problems, and also the sub problems is sub problems is dependent because when we get the number n, we have multiple options. So when we choose 9 as a number to subtract, the remaining would be 3. On the other hand, when we choose 4 as a subtract number, we get 8. So the sub problem would changes depending on the first choice. Okay, so that is so the dynamic programming works here, I think. Dynamic programming. And for dynamic programming, we have two options: top down or bottom up. Top down means we can use recursive function and memorization. I see. Perfect number contains 1, so we can make sure there must be valid solutions. But the program requires us to return the least number, so we have to use the larger number as much as possible, because in order to get the least number of perfect square numbers. Okay, we have to return the length of the perfect square numbers we used. Okay, so the basic strategies. For example, it's 10,000. So okay, this is also perfect squares. So we can prepare perfect squares at first, right? For I in range 1 to 100, and perfect squares append I times I, that's a perfect squares, and not too long. Yeah. Yeah. And yes, we prepare the DP arrays and in order to store the least number to achieve the n, to achieve store the least numbers that can achieve the n, achieve the target number. No. We use DP array to store the least numbers that sums to the target numbers. So DP n can be DP n minus k. K is one of the perfect square number, and increment 1, because we use one number from the perfect squares. So yeah, the subprogram is like this. And ideally we want to use the numbers from the larger side. How do I implement? And what is the base case? DP st, yeah, times 5 times n. DP has n elements, and plus 1 and plus 1, because we want to achieve n. and dp0, we can achieve zero number. We can achieve it with zero perfect square numbers. Here's a base case. Number in perfect squares. We update the dp num 1. Okay. But this is not good. What do you think? Yeah, let me try a top-down solution. Yeah, num imperfect squares, and the target would be minus num. Count. Okay, we want to gradual one. So we have index to store the to point the perfect squares. It's valid. If it's valid, we use it. Index out of range. Oh, I see. UISDP. We don't need TP. We use recursive. Wrong answer. The output is 100,000. Answer count. Oh, we didn't call recursive. Target n, count 0, index 0. Runtime error. Why? Cannot access local variable ans where it is not associated with a value. Huh? Really? We can't do that. Oh, I didn't know about this. Oh, really? Once we declare once. Same error. Unbound. Eh? Really? Integer. Unbound. What? 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 Really? Current answer. Use list to avoid scoping issue. I didn't know that. Wrong. Ah. Oh, correct. But I'm not sure this is efficient. Since we specify the index, so we, yeah, I feel like we eliminate the duplicates. No. No. But how do I casting? There is a target and count. Let me submit it. Time limit exceeded, okay. Oh, accept it. Lot of duplicates. Target. To casting. Target and yeah, target should have memo should have a minimum count and target for the key. So and the count return it's less than the value in the cache, it might be update the yeah. It's memos. Target none. Yes, but sometimes we cannot achieve the target. Yeah. Wrong answer. What? Oh, I see. This is nonsense because when it returns okay, result. Memos target 1 plus return result. Like this. We don't have to answer. Right? How about this? Great. 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 Oh, it takes long time. Oh, really? What is Hmm? 88. Oh, okay. So this is not good. Time limit exceeded happen in early phase. Oh. Oh. long it took. Try again. The result depends on both target and account. It's almost the same. It's almost same. Is this not good? While we can return it. If the target is 0, we do nothing, so we can return 0. Okay, and the result perfect squares. I see. One plus. How about this? Oops. Okay. Not bad. Oh, but they are. Check. While check. Prevent. Check. Perfect square. Check means target number. Check has a target number as a set, and count we have to check. Append the candidates as a target and update the check set. I didn't understand why this is so fast. Oh, this is cool. This is cool. I mean the square numbers and then square numbers plus 1. It should be J. I wanted to come up with this solution. It's bottom up solution. Cause minus I means perfect square. So okay, we initialize the DP array with infinite, a large number, and DPI means the least number to achieve. Yeah. That sums to I. The least number of numbers that sums to I. No? We use perfect square numbers. We can use n plus 1 for every perfect square numbers. We want to check but it starts with I. I see. It means, for example, the n is 120. It checks like this. Because in order to achieve 2 or 3 or 4, 2 or 3, we cannot use 4 or more anymore. So we checking it starting with square numbers. So the time complexity be square root n times n. Yeah. Okay, I understand. Okay, I got exhausted. Finish